Let's now take a quick look at a more contemporary counterpart of exploratory factor analysis, confirmatory factor analysis. Here on this introductory slide, you can see an example of a path diagram that reflects the results of a confirmatory factor analysis. And as you can see, we here have our variables reflecting some negative symptoms and some activities that people have reported. And we have latent factors. Some of them are dependent. They are predicted by other latent factors. And one is independent quality of life. It's a more general factor that is kind of the general dimension. And each of these dependent variables, either observed or latent, they have these little circles attached to them. This is essentially a measurement error or a residual covariance. And this one for a latent factor, the same thing is called disturbance. Basically, it's part of its variance that is not explained by its predictor, by its parent factor, so to say. And some of these measurement errors can also correlate, where they reflect the reasons why, for example, two symptoms like nausea and vomit can come together when there is no pain. So maybe not all physical problems are connected with this pair. Yeah, and that's how you normally present these results. But what do we use confirmatory factor analysis for? Our main task is to test a hypothesis about a latent structure of a set of observed variables. So my question that I ask when I do this CFA, does this model explain all the shared variance of my indicator variables? Does this factor model capture all the information that is important about my variables in this data set? And unfortunately, exploratory factor analysis does not allow us to answer this question well. And even in the packages where you see fit indices for EFA, still the model contains all those extra loadings that you don't really need. And as a result, these fit indices are not quite trustworthy. So that's why CFA was developed. And nowadays, it is a method number one, which is used always to validate the latent structure of a new questionnaire. Now, it's not enough to conduct an exploratory factor analysis. Obviously, for a master's dissertation, it's probably enough. But if you want to publish your research, you probably want to conduct a confirmatory factor analysis. And sometimes we even test confirmatory factor models where latent factors are based on indicators from different questionnaires or different sources of information. For example, when we want to establish validity of some kind of measurement procedure, we try to separate the effects of trait from the effects of method, because we know that all self-report questionnaires correlate because of response bias. And we create a multi-trait, multi-method latent factor model, the example of which I showed you in our discussion of validity in lecture 4. And sometimes when we develop questionnaires, we also try to separate latent factors corresponding to bias. For example, a tendency to agree with all the items, or item direction, or social desirability. We can definitely, if we have good indicators, we can separate these dimensions using CFA. And another very large and important area is testing of measurement invariance. Does my questionnaire have the same properties if I use it in samples of Russian-speaking and English-speaking people? Or does my ability test have the same properties in the samples of males and females? Is it fair? Or does it discriminate people from one group? So to answer this question, we conduct this multi-group CFA. And sometimes we can use this latent model to derive factor scores that will be much better, much more precise than raw scores that we could calculate based on just summing up all the items. What are the assumptions of confirmatory factor analysis? Well, essentially, it's very similar to exploratory factor analysis. It also uses a covariance matrix, not correlation, but basically there is no difference. It's still multivariate normality. Here you need at least 2 indicators per factor to identify your model. But if you only have 2 indicators, it's somewhat risky. If one of them doesn't work well, your model may actually fail to even converge. That's why it's best to have at least 3 indicators. But also if you have too many indicators per factor, like you have maybe 20 questions per a single scale, it becomes problematic, because the more questions you have, the more potentially associations they can have among each other due to some reasons not related to your latent factor. Like, for example, 2 questions use the same word, and there will be some error covariance as a result, and it will be challenging. So it's best to have 5 to 7 maybe items in a scale, optimal for a CFA. And in terms of sample size, the good news is that having about 200 people is generally considered sufficient for most purposes. And even smaller samples, even samples of 100 and smaller, have been used in the literature. But in smaller samples, obviously your confidence intervals for loadings, for fit indices become huge, and it's very hard to rely on these findings. But this is in contrast to exploratory factor analysis, where the number of people you need is proportional, maybe not linearly, but is related to the number of variables in your model. And in confirmatory factor analysis, it's actually vice versa. The more variables you have, the more degrees of freedom you have, the more information you have in your data, and the more trustworthy your model becomes even in smaller samples. So we give confirmatory factor analysis our expected theoretical model, and as a result, we get, first of all, fit indices that tell us whether this model fits our data. There are a whole bunch of different fit indices. Actually, in the literature, the textbook by Timothy Brown, Confirmatory Factor Analysis for Applied Research, is the best source nowadays. And basically there he recommends that having 3 fit indices is enough. CFI, comparative fit index, that compares your model to a model that explains your data perfectly, and a model that explains absolutely nothing in your data. So a model that explains your data perfectly is 1, and a model that explains absolutely nothing is 0. And comparative fit index shows where your model is on this dimension. And if your model has a comparative fit index CFI of 0.95 or above, you can rejoice. It's a really, really good model. But if it's above 0.90, it's acceptable. If it's below 0.90, maybe it's a little bit problematic. So CFI, the higher, the better. And for the other 2 indices, RMCA and SRMR, root mean square error of approximation and standardized root mean residual, basically these are residuals, unexplained associations. So the smaller they are, the better. And if RMCA and SRMR are below 0.05, it's a very good fit. And if they are below 0.08, it's acceptable. But don't be extremely careful about those specific values, because in different data sets, they might not be quite optimal. For example, generally, if you have a large number of variables, you will tend to get worse CFI values and better RMCA values. And simulation studies show that these indices are somewhat dependent on the number of variables, factors in your model, how strongly are variables correlated. So that's why they should only be interpreted in combination. If like one index shows you a really good fit and another one shows a fit that is so-so, probably it's still a good model. But of course, if all 3 indices show you poor fit, it's very hard to justify such a model. And of course, in addition to these fit indices, we also get estimates of our factor loadings, covariances between factors and between item errors. And we also get modification indices. What additional parameters could we include into the model to improve the fit? Well, let's now see how it works. Unfortunately, you cannot conduct a CFA in SPSS because it's handled by AMAS, a separate bunch of software. But in Jamovi, there is a nice module for confirmatory factor analysis, which is very easy to use. It is limited in its capabilities. It only allows you to test very simple models using only maximum likelihood approach. So if you have some categorical data, or if you have some strong non-normality, maybe you need some package that would be more robust, either R or M+ or AMOS. But for many situations, for many purposes, this is quite sufficient. Another limitation is that it only shows you these path diagrams without actual numbers, so you have to draw this path diagram by hand. But, well, I have not seen a single software package that would produce a path diagram that would be publishable. Even the best ones like M+ or EQS, they still produce diagrams where you need to redraw them by hand to make them publishable. So what you do here is basically you click on add new factor, you give it a name, and you drag and drop variables that you expect to be indicators of that factor. And you don't really need to set even anything. Well, the only thing you need to set is ask for standardized estimates, because in confirmatory factor analysis, since it's based on covariances, it's just like in regression. You have unstandardized and standardized parameters. And it is normally standardized parameters that you're interested in because they are easy to interpret. So the results of our factor analysis are basically these two little tables. The first couple of tables are called model fit. And here we have a chi-square statistic, which is also called test for exact fit. If chi-square is not significant, it means that your model fits your data extremely well. And in path models, where we have small number of degrees of freedom, we tend to rely on chi-square test. So if you have less than 10 degrees of freedom, then chi-square test is your best source of information about model fit. But in factor models, where we have a large number of degrees of freedom, like here we have 169, chi-square is almost always statistically significant. It's not very informative because it detects very trivial deviations from explaining your data well. That's why we look at our fit indices or practical fit indices. So here we have CFI, which is completely unacceptable. If it used to be close to 0.90, we could maybe argue that it's acceptable, but no, not this way. And RMCA is also above 0.08, which is outside the range of acceptable, but it's fairly close, which means that it's not a very bad model, but maybe it's missing something. And SRMR indicates acceptable fit. But unfortunately, these two are more trustworthy and they are better studied as well. So in combination, we say that this model does not work. We have some unexplained shared variance. But if we look at these factor loadings, we see that they are all quite all right. There are no variables with very weak or non-significant loadings. All of them are above 0.4 at least. And irritable obviously is the weakest, as we've seen before. So it's not a bad model. So what is missing in this model? Either loadings on other factors or some associations between variables that are not explained by factors. And in order to understand what is missing in this model, we use modification indices. What are modification indices? Essentially, Jamovi or any other software package, it tries all possibilities of adding one parameter to your model. So what would happen if I add one factor loading? What would happen if I add one error covariance? And it tries all those possibilities, and for each of these possibilities, it conducts a chi-square test, which tests whether the improved model will fit the data significantly better than the model without this parameter. As you can see, this approach is actually quite stupid because it tries all possibilities. It does not know which of them work, which don't. And also, for each of them, it conducts an independent chi-square test. As we know, there is the problem of multiple comparisons. If you use a weak cutoff criterion, for example, p less than 0.05 for this chi-square test, you risk getting many modifications just by chance. These modification indices, basically they are chi-square values for 1 degree of freedom, and the minimum significant one is 3.8 for p less than 0.5. In very small samples, you can consider modification indices of this magnitude. But in larger samples, I recommend to consider modification indices above 10, sorry. This is the default in M+ and in many other packages. And the logic is that above 10, these modification indices are likely to be significant at p less than 0.001, and the chance of getting a false positive result is acceptably low, unless you have thousands of them in your model. Yeah. So basically in Jamovi we tap modification indices, and we do it in this post hoc model performance little dialog. And then basically for every possibility to add the parameter, it gives us this chi-square value. For example, what would happen if we add some factor loadings? These are all positive emotions. What happens if they get loading on negative emotion? Or these are all positive emotions. What happens if we give them loading on negative emotion? And when we interpret these modification indices, we look for the strongest ones. We look for outliers. And here for factor loadings, there is probably just one outlier, this scared. And the software proposes us to introduce a factor loading of scared on positive affect. But can people say that they are scared because they are experiencing positive emotions? I would not buy that as a reviewer. So I would never add this modification into my model. And you should be very careful about modifying your model based on these suggestions, because sometimes they're completely meaningless, sometimes they are completely stupid, and they can screw up your nice theoretical model. If you can avoid introducing modifications, please avoid, because your model, even if it fits the data slightly worse, it will be more theoretically justifiable. But these were modification indices for just the factor loadings. What happens for error covariances? Error covariances are basically associations between pairs of variables that are not explained by latent factors. Sometimes we get them when two variables have the same word or a similar formulation, or just because of position effects. For example, we have two questions from a questionnaire on one page, and then all the other questions go on different page. This can happen sometimes. And here again we see all these possibilities of adding an association between unexplained variances of pairs of variables. And we start by looking at the outliers. We start by looking at the strongest ones. Ashamed and guilty makes sense. Upset and distressed, scared and afraid, determined and inspired. So as you can see, these are pairs of emotions that reflect kind of similar emotions. They seem to be substantially meaningful. So we can consider adding them to our model. But then if we add them, we would need to cross-validate our model in a new sample. That's why instead of maybe relying on our modification indices, we can rely on previous research. And we can dig up a paper validating this PANAS measure in another breach sample. And there people performed a content analysis of those items, and they said, okay, let's just include covariances for pairs of items that reflect the same basic emotion. Like, for example, hostile, irritable, it's anger, scared and afraid, it's fear, nervous and jittery, it's some kind of activation, and so on. And we can basically just add all these error covariances into our model. In the dialog residual covariances, we choose two variables and we drag them to the right. As a result, this error covariance is added to our model. And what happens if we add all of them, all 13 of these covariances? Our fit becomes much better. Chi-square is still significant. We don't care about it. The number of degrees of freedom has decreased by the number of parameters that we added, 13. But fit measures, look at them. CFI is now almost 0.95. RMCA is 0.06, which is considered already good fit by Hugh and Bendler. So this is quite an acceptable model, and it's also justified by prior research, even if some of these residual covariances are not significant. For example, interested with attentive is kind of almost significant, but interested with alert is not significant, and so on. So maybe this theoretical hypothesis of Crawford and Henry was not perfect, because even after adding all those covariances, we see that some of them are not significant, but the modification indices remain for determined and inspired, for example, suggesting that maybe it's some kind of inspiration or motivation, and for excited and interested, suggesting that, well, if I'm excited by something or about something, that's maybe some kind of object. Yeah, so in principle, we could consider revising this theoretical model. But again, if we introduce any modifications based on our data, ideally we would need to cross-validate this. Otherwise, reviewers are not going to buy it. Okay, so I hope you've got the general idea of how confirmatory factor analysis proceeds, and you can perform CFA in Jamovi for your own questionnaire if you want to develop it. Of course, if your model is not completely theoretical and if it's based on some exploratory procedure, for example, you did an exploratory factor analysis and then confirmatory factor analysis, it is a bad idea to do it in the same sample. Because in the end, in confirmatory factor analysis, you are testing the same hypothesis that you came up with based on the same data. So it's very easy in this process of modifying your model based on your data, it's very easy to capitalize on chance and to introduce into the model parameters that are related only to this particular sample, but that don't replicate in other samples. That's why the good approach is either to rely on a theoretical model and introduce a minimum number of modifications, or just split your sample randomly. If it's a large sample, you can split it into parts which you'll use to explore and develop your model and do exploratory factor analysis, and another part which can be smaller where you can do confirmatory factor analysis to test whether the resulting model works. But of course, you need to be honest in this and just split it once and put aside the other portion. Don't play with it until you have finished playing with the first portion. Otherwise, the whole process loses meaning. So this was a little introduction into confirmatory factor analysis. Some special issues. Our standard confirmatory factor analytic model does not always suffice for our research purposes. One situation where we might have a problem is a situation where we have a common construct and we have kind of subdimensions. For example, you have there are many famous questionnaires with forward scored and reverse scored items, like life orientations test. In uncertain times, I usually expect the best forward scored item. I don't expect that my future will be bright, a reverse scored item. And if you do exploratory factor analysis, you will see basically two factors. You can call them optimism and pessimism, but in fact, they are both about optimism. It's just the formulation that is flipped around. And the question is, does this questionnaire contain one dimension, or are these two independent dimensions? So if you want to justify that you want to calculate a total score based on a questionnaire with forward scored and reverse scored items, what you normally need is called a bifactor model. A bifactor model which separates the variance shared by all items in a general factor from variance shared by subgroups of items, for example, because of their direction, because they are forward scored and because they are reverse scored. In fact, it's not complicated. It's also probably even possible to test it in Jamovi, but you need to remove the factor correlations, because these factors in a bifactor model, they are supposed to be uncorrelated. Otherwise, the model may not even converge. And just as an example, coming from our recent study with Olga Gulevich, where we studied attitudes to LGBT people, and there was one questionnaire which measured group entitativity. Basically, a belief that LGBT people, they have a single group that organizes its actions. And there are two components there, similarity and organization. And but you can imagine that these are forward scored and reverse scored items. It will be the same type of model. So here we have a two-factor model where we have one item which kind of contributes to both constructs, and we have one error covariance. And these factors are fairly strongly correlated. But if we want to calculate a total score for this questionnaire, what we would need to justify it is to test this kind of model on the right, where we have one factor that contributes to all the items and two factors that contribute to groups of items. It's okay if some of these loadings here are not significant. It's fine. What's important is that these loadings are supposed to be significant. And if this model fits the data well, here it fits the data even better. You can even calculate reliability coefficients for these dimensions separately to see how much variance do they capture. It's not quite straightforward, but these papers by Rice and colleagues, they explain it all in detail. So this is the kind of model that you might need. But remember that these factors are supposed to be uncorrelated with each other. Otherwise, it will not work. And some other developments in this field of confirmatory factor analysis that are happening recently, they try to work around another problem. And this problem is that sometimes we have questions that have substantive relationships with several factors, that have these cross-loadings that are not errors, not artifacts, but they are quite logical. For example, let's take a question from the Big Five inventory. I like being around people. Originally, it's supposed to measure extraversion, its aspect of gregariousness. I like companies, I like socializing, and so on. But it also captures, to some extent, it is influenced by agreeableness, because some people might answer yes to this question because they're generally nice and they like talking to people because they like people, and not because they like fun and excitement. And maybe even openness can influence, because some people can say yes because they like meeting new people and learning new stuff from those people. So this item might be related to several Big Five dimensions at the same time. And if you apply confirmatory factor analysis to such a data set, CFA will impose its unrealistic assumption that all the cross-loadings are zero. Only the loadings that are present in the model are statistically non-zero. But in fact, this assumption is kind of unrealistic, as is argued by many authors. And even if a question is not related to a factor, its loading might not be exactly zero just because of sample bias. And we need to introduce this possibility for the loading to wiggle a little bit around zero into the model in order for our model to fit the data better. Unfortunately, CFA does not allow us to do it easily. As a result, in CFA, we get overestimated correlations between factors. And we have problems with questionnaires where we have many items with very diverse item content. The Big Five is a classical example. These questionnaires work extremely well with exploratory factor analysis, but with confirmatory factor analysis, they might fail to show a good fit. questionnaires like Zimbardo time perspective inventory, and other questionnaires with a large number of items that are very diverse. What can you do to remediate this situation? You can use two newer approaches. One approach is called exploratory structural equation modeling, and it's basically a type of model shown here on C, subpart of this diagram. Essentially, it's the same as exploratory factor analysis, because all the variables are connected to all the factors. But the difference from exploratory factor analysis is that you can tell the statistical package which loadings you expect to be high and which loadings you expect to be close to zero. And the rotation algorithm will try to adjust your position of your axis in such a way as to approximate this theoretical expectation. And this approach works fairly well, because then you can start trimming these redundant loadings and so on. So you can do many things with ESM. It's very flexible. Another very new and very promising approach is called Bayesian structural equation modeling. And here you can see it on the subpart D of this diagram. Essentially, it's pretty much the same. All variables are connected to all the factors, but for the theoretically expected loadings, you set expected size of this loading prior in Bayesian terms. You say, okay, I expect this loading to be around 0.7 with some standard deviation around it. And for all the other loadings, you say, okay, I expect these loadings on other factors, on these dashed lines. I expect them to be on average 0, but there is prior with some standard deviation. So I give the algorithm some wiggle room around this 0. And as a result, they can sometimes occasionally be even statistically significant. But this model is much, much more flexible, and it can be more realistic in terms of what it assumes about our data. Also, it correctly estimates correlations between the factors, which helps us to show discriminant validity. But unfortunately, it's a bit tricky to apply. It's not available in Jamovi and, of course, in SPSS. And even in R, Lavan, I don't think it does ESM yet. If it does, please let me know. So far, these models are available mainly in M+, which is unfortunately commercial, but still it's a very promising direction. And it can help cope with situations where conventional CFA does not quite work. So now there are many more publications showing the structure of the Big Five using ESM and Bayesian SEM. But just a couple of words. What is SEM? What is structural equation modeling? Basically, it's this whole general framework in which you can test all kinds of models. You can test models with observed variables only, like correlation or regression, when these variables start predicting one another. And basically, this is the difference between confirmatory factor analysis and structural equation modeling. Because confirmatory factor analysis and exploratory factor analysis, these are models where variables are connected to factors, but factors freely correlate with one another. So essentially, it's like a correlation of latent variables. And if you start introducing some regressions of latent variables on one another, what you're doing is better called structural equation modeling. Unfortunately, it's not yet available in Jamovi, so I will not go into many details. But if you do it, remember that don't start with the very complicated model. Start with the simplest model. Start with a CFA model or measurement model, it's also called. And only then, if it fits the data well, proceed to introducing some kind of regressions of factors on one another. And essentially, it's just like path models, but with latent factors. So here, this example comes also from the same paper with Olga Gulevich, where we modeled different components of prejudice towards homosexual people. And here we see that perceived threat of homosexual people is higher in those who believe that homosexuality is contagious, and it also predicts the tendency to not to protect and not to support them, but to treat them medically and to punish them, to put them into jail. And this is completely mediated by this perceived threat of homosexual people. And this model fits the data well, but obviously you can place this in a different sequence because it's a cross-sectional study. Yeah, so this was just a little introduction into confirmatory factor analysis and structural equation modeling. In some programs, you will have additional courses on that. If you learn it yourself, it's also not so complicated. Now there are many good tutorials online. Just remember that when you play with structural equation modeling, an infinite number of models can fit the data equally well. So your model is supposed to be based on your theory. If you can justify it by theory, you can publish it. If you can't, better don't. And if you modify your model, also be very careful about this, because I have seen in publications so many stupid, meaningless models where people have included so many errors that the whole model lost its sense, its theoretical sense. So it's better to have an economical, parsimonious model which is based on your theory, even if your fit is not perfect. Okay, so this was a little introduction into confirmatory factor analysis.